All right, kia ora and good afternoon, everybody, and welcome to the Beca Connects Space and Situational Awareness webinar. On behalf of Beca and SpaceBase, welcome to this monthly series focused on space and the information domain within the New Zealand context. I'm Brendan Pett. I'm going to be your host for today. I'm the Operations Manager for our Trans-Tasman Defence and National Security business and the Beca lead for space. Today, in our sixth of the series of webinars, we're looking to space situational awareness, and we'll be hearing from presenters from the Defence Technology Agency and LeoLabs. For our audience, while our speakers are presenting, please feel free to submit questions via the Q&A tab, which should be on the bottom of your Zoom screens. We will be holding questions until both speakers are finished and then presenting through the series of questions that we have. So on to our first speaker. I'd like to introduce Jovan Skulan. Jovan is a scientist with the Defence Technology Agency, or DTA, based in Devonport, Auckland. Born in Belgrade, Serbia, he completed an undergraduate studies in astronomy and worked for a few years as a teaching assistant at the University of Belgrade. He received his PhD in astronomy from the University of Canterbury there in Christchurch, where he also worked as a teaching and research fellow. Jovan joined DTA in 2004 and over the past several years has been involved with the space situational awareness, including the development of DTA's SSA Observatory, as well as SSA data collection and analysis. So please welcome Jovan.
Thanks, Brendan. Thank you for inviting me to talk to you today. I would like to present some of the recent results that we have achieved in the area of space situational awareness. I work for the Defence Technology Agency, which is a small unit of the New Zealand Defence Force. We basically support the NZDF by providing technical and scientific advice. Unfortunately, I will not have time today to talk more about various research areas at DTA, but I would like to invite you to visit our website, where you will see these main research groups and where our space program fits in. However, there have been some changes recently which might be available on the website as well. Now, before I start talking about our work and space situational awareness, I wanted to share with you this home video, which I took one evening from my house, looking southwest just after the sunset. You will see some street lights on the road below, and you will see that the sky is still not completely dark, but there is a single twinkly star in the sky, which is, I'm sure you recognized, Alpha Eridani. If not, don't worry. The main action was happening lower on the horizon, and very soon you will be able to see a faint object in the sky. That's International Space Station rising. Now, you can try this sometime by yourself. It's fun. And by doing that, you will become involved with space situational awareness. You can even use a simple video like this to get useful measurements out of it, such as the position and brightness of the satellite. You will see that the motion is very slow at first, but the satellite picks up speed and the brightness. I'm not going to suggest that we should now use smartphones for space situational awareness, simply because I don't want to start a war between Samsung and Apple about whose phone is the best for SSA. What is space situational awareness? I want to show you this image, which appeared in a recently published document by the Defense Intelligence Agency in the US, showing that basically space situational awareness is a collection of different techniques and technologies used to track satellites in orbit, such as radar, which we will hear more about from Terry later, optical facilities, laser ranging facilities, and I don't know if you can see behind, I can't see behind all the camera views. There is also radio frequency stations. And also on top of that, we have space-based SSA, which can in principle utilize all of these technologies as well. Just a quick timeline of the development of the space situational awareness capability at DTA. We started in 2015 by, it was a joint trial between DTA and the UK equivalent, DSTL, trying to observe the deorbiting of ATV-5, Automated Transfer Vehicle 5, by the European Space Agency. The plan was to travel to the South Island and observe this from multiple locations, as you can see from these beautiful pictures. As it happened, we never saw the deorbiting of ATV-5 because it was cancelled by the European Space Agency, and we ended up observing other satellites, collected plenty of data. You can see a nice shot of a satellite approaching the Large Magellanic Cloud one night while we were there. The following year was dedicated to the development of our data analysis software tool called StarView, which has grown considerably since then. It was subsequently upgraded several times, and it's now a very complex and useful tool that we use to analyze our data from all orbital regimes. Back in 2015, we found that even using the very wide field off-the-shelf equipment, cameras and lenses, we were able to achieve quite good astrometric accuracy of better than 15 meters in space at the typical range, low Earth orbit range of 500 kilometers. Then in 2017, we upgraded our capability by building a small dome observatory. We added a tracking mount and a telescope for fainter objects. We also built a specialized polarimetric camera called QuadCam that was able to record light in 4 polarization planes, demonstrating then that polarimetry adds additional information that cannot be obtained from photometry alone, but we didn't continue that work much further. Sorry. The 2 years after that were dedicated to photometry, mainly photometric work measuring the brightness of satellites in geostationary belt. We ended up with plenty of light curves, such as shown here, that showed interesting features and light variations during the night. That was complemented by a 3-dimensional photometric model of a satellite in orbit, enabling us to compare the predicted amount of reflected light with our measurements. And this was done in collaboration with Canada. And finally, the 2 years of Phantom Echoes. Now, if you've never heard that name, Phantom Echoes is a collaboration group between the Five Eyes nation, Australia, Canada, New Zealand, the UK, and the US. And it was focused on proximity operations in GEO. And as a very nice, convenient case study case, we picked the Mission Extension Vehicle 1 and 2, operated by Northrop Grumman, which were designed to approach and dock to other geostationary objects for maintenance. Especially the first one, MEV1, was of importance to us because it was clearly visible. It was in clear view from New Zealand. It was taking place over the Pacific. We took a lot of data on that. I'll show you that in a minute. But the second mission in 2021 was a bit different. We were involved mainly in the early orbit raising phase, but not so much during the actual docking operation, as it was happening on the other side of the globe over the Atlantic. And towards the end of that year, we started our work on calibration, astrometric calibration, which I will also mention in a minute. Just wanted to tell you here that during this year, we were joined by University of Auckland, the Space Institute, in particular the Orbital Dynamics team, which enhanced our ability to analyze the data from this experiment. Just briefly where we are. Driving from Devonport to the observatory takes about an hour, which you wouldn't want to do on a daily basis, but it's convenient when there is an urgent maintenance required. A summary of our equipment. The latest setup is shown on the right, with 2 telescopes mounted side by side for a selection of fields of view. So we use that these days to track satellites in all orbital regimes. So just to show you some of the results from recent years, and I'll start with Phantom Echoes 1 and 2. As I mentioned already, Phantom Echoes 1 was happening around the Pacific, so it was perfectly positioned for us to take measurements. So here you see a film strip of some images taken during the night on the 24th of February 2020, when the actual docking happened. We didn't see the last stage because our observations were interrupted by sunrise, but during the night we saw clearly the 2 satellites approaching each other up to the point where they were only a couple of 100 meters apart. And our astrometric measurements, which is the position of the satellite of MEV1 with respect to Intelsat 901, are shown on these charts. Also the photometric measurements, dramatic changes in brightness during the night, because the satellites were both aligned accurately to dock to each other. On the last night, there was a brief interruption due to an eclipse of 20 minutes, which you can see here. Both satellites disappeared from the view, but then they appeared and showed multiple variations in brightness, which was very interesting to observe. To give you a flavor of some of the images that we took, this is a video made up of a few dozen images taken on the on November 19, actually, while MEV1 was in an early orbit raising phase before the docking operation. But later in 2020, here is a video that I call Flyby. It's a compressed video of a few hundred images taken over 6 hours of MEV1 passing very close to Intelsat 901. And this is the final approach. There is the eclipse. Then after the eclipse, First one to appear is MEV1, very much brighter than Intelsat, but then there were multiple changes in brightness as the satellites were carefully aligned. This is also a few hours of observation compressed in just a few seconds. And towards the end of the night, both satellites appear more or less the same brightness, as both have the same alignment of their solar panels, and they appear the same in brightness. So using data like this, it was possible to do a lot of analysis, which I won't bother you with. It was all published, and it was part of our joint report with the other 5 nations. I just want to show you a bit more about our photometric modeling, because that's another aspect of our work. This is more about measuring the brightness of a satellite and trying to figure out how the various parts of the satellite are positioned in space to get the amount of light that we detect. So basically, the model treats a satellite as a collection of small flat facets that reflect light towards the observer. Don't worry, I'm not going to talk about these equations. This slide is mainly here for completeness. Apart from the direct sunlight, the satellite also reflects the light from the Earth below, which we call the Earth shine, and that can be a significant contributor to the total brightness. It's a very complex thing to model because there are variations across the globe. There are variations depending on the season. And basically, we use satellite data from a mission like GOMER-1 to integrate the brightness of the Earth for the time of observation. When all that is in place, then you can model your particular satellite. And just as an example, I'll show you here how the brightness obviously changes during the night, just because the different parts of the satellite change their aspect angle with respect to the observer. Now, on the left side, you see the view from the observer. The middle is the view from the sun to see what part of the satellite is actually illuminated. And on the right, you see what the satellite sees, the Earth below and our little observatory here where the circle, yellow circle is. But as the time goes, if you pay attention to the left-hand panel, you will see how the brightness of the solar arrays dramatically changes as the time goes, because the solar panel tracks the sun. However, the 2 side panels, they also change their relative brightness. I'll go back once and forward again. So all these changes are clearly visible in our measurements. I'll show you a light curve that was recorded on one of the nights, and you can see the brightness changing. On the left-hand side, you see what we call the apparent magnitude, which is used by astronomers. The lower the number, the brighter the satellite. Our initial model was able to track down these changes quite well by assuming that the solar arrays have a small offset angle. They don't point directly at sun, but about 8.2 degrees off to match the position of the central peak. Now, interestingly, there is a lot of deviation towards the end of the night, which was a sign of a change in this offset angle. And it turned out that if we introduce the change of only 5 or less than 5 degrees here and a few degrees at the beginning of the night, we get a model that follows the data more closely, demonstrating that modeling the photometry like this enables us to tell more about the relative orientation of different parts of the satellite during the night. And to close my presentation today, I want to show you just one slide of our calibration data, showing the capability of the ability of measuring the position of the satellite to a high accuracy when compared to the predicted orbit. So for this, you need to choose a satellite that has accurately predicted orbit, and in this case, it's one of the GPS satellites called Navstar 73, which was observed on 17th of January. The satellite is shown here as a dot and some stars around, used to measure its position. Our measurements show very low scatter of, you can see, about less than quarter of an arc second, which is enough for very fine adjustments, for very fine analysis on, say, perturbations in the orbital motion of these objects. But the main reason for doing this for us was mainly to get an idea of the quality of the data when sharing our data with other nations within the collaboration. I think this is my last slide for today. I'm eagerly awaiting for your questions, so thank you very much.
Thanks very much, Jovan, and I'm sure a lot of our attendees are probably relieved that they won't have to recite your mathematical formula there, or that there'll be a short test at the end. So thank you very much for that. I just remind our attendees to submit your questions via the Q&A function at the bottom of your Zoom screen, and both speakers will have a chance to answer those questions after we've heard from our next presenter from LeoLabs. So I'm now delighted to introduce you all to our second presenter on SSA, Terry van Haren. Terry is the Managing Director of LeoLabs Australia, a subsidiary of LeoLabs Incorporated. Terry joined LeoLabs after a very distinguished 35 years of service with the Royal Australian Air Force as a commander, director, fighter pilot, and weapons officer. Terry's last RAAF assignment was as the Air and Space Attaché to the United States. Terry believes that cooperation between government departments, space agencies, and commercial industry is the key to space safety, security, and prosperity for like-minded space nations such as those of Australia, New Zealand, and the United States. So please welcome Terry.
Thank you, Brendan. Yeah, good day, everyone. It's a great pleasure to be here today. So thanks for this opportunity to talk to through the webinar. And as Brendan highlighted there, I'm more of an operator. So if we get any hard physics questions at the end, I'm going to hand them over to Jovan. But just about to advance my slides here, hopefully. So the big picture on LeoLabs is a company which has come out of the United States. Hopefully you're reasonably familiar with LeoLabs because you do host our third radar system in the South Island of New Zealand. But LeoLabs came out of Stanford Research Institute in California in 2016. It was researchers looking at astrodynamic problems, advanced radar and phased array radar systems, and also working for some US government programs to look at how to scale and keep up with the rapid change that's occurring in the space environment, especially with what we call new space or space 2.0. And that's the growth of the commercial industry, especially in low Earth orbit. It was only last year, in fact, we started LeoLabs Australia when I returned from the United States. And as one of the subsidiaries, of course, there is a New Zealand entity there that manages the radar. We have a growing list of customers around the world. We've had strong adoption from the US commercial satellite industry. Our biggest customers there are SpaceX and OneWeb, plus Planet, Maxar, and a few others. And in fact, we say now we're providing track monitoring collision avoidance services for the operators of over 65% of the active satellites in low Earth orbit. So we're fairly proud of that situation there. On the government side, we've been a data provider to the US Space Force through the Unified Data Library, and we've just recently announced that we're supplying data and training services to the Japanese Ministry of Defence. Back in New Zealand, a very advanced space agency as far as I'm concerned, are really our first users of our, what we call our regulation and compliance tool set. It's a specialised tool set there on our platform that allows the New Zealand Space Agency to ensure that the satellites that they've registered in orbit are compliant to those orbits. And we're also supplying data to the UK Space Agency. So we hope this list grows, of course. We sell our services as a service. So these are all subscriptions, and that's returning subscriptions is really the way we measure success in this type of business. With the next slide, I'll just quickly tell you what we're trying to achieve. And we say we're the end-to-end mapping platform for space, but we're vertically integrated. We own and operate our own radar systems. We collect our own data. We then aggregate that data and produce a whole bunch of different products there for both the commercial and government and defence type of parts of the space industry. Our aim is to drive transparency into the low Earth orbit environment. And we do that to really promote sustainability of that environment and deterrence. We are independent of governments here. So in debris monitoring, for example, we will show what's going on in that sense. And we did call out early in the piece the Cosmos 1408 breakup after the Russian ASAT last year. And our ultimate aim here is to grow the commercial space industry, support it, across all users there, and give them a data advantage of operating in this very dynamic environment. I'll go through some of these products on the live view. So, and try and make this a little bit more interactive. If I can just get control, I'll enable to share my screen. Okay, so it's not going to let me do that in the webinar view. I'll talk quickly then about a few of these aspects on this page. Firstly, the radars that we own and operate. You can see the 4 sites that we have there. In fact, there's 6 radars. The earliest one was the one in Alaska, which is a flat-faced phased array radar. And it was really our research radar that we developed the algorithms and system processing that has become core to our system. Midlands, Texas was our first space fence type radar, one-dimensional search, and basically a proof of concept radar. But in 2019, we built the Kiwi space radar in the South Island in Otago area. And it's our first of our S-band radars. Now, S-band is important for us. That's around about 3 gigs. The wavelength is more important, around about 10 centimeters. And S-band gives us the ability to see the smaller objects in low Earth orbit. If you know the basic physics of radar, these radars are designed to see objects down to 2 centimeters or golf ball size in low Earth orbit. The Costa Rica radar is the last picture on the bottom there. And it's you can see there's 2 parabolic dishes. That's actually one radar. This is a networked radar. It's interferometric, so basically one of these parabolic structures is transmit and receive, and the other one is receive only. We're measuring the signal twice to improve the accuracy and the sensitivity of the radar. And so on each of our dual sites, we actually have 4 dishes set up here. It looks like I've got screen sharing back. So I'm going to take you to the live platform now. And this is where you'd normally log in for a subscription. The first thing, I've sort of covered the radar. So I'm going to take you straight to the visualization of what we do and the mapping product, if you like, in low Earth orbit. So our radars are globally distributed. What we are doing is every time objects fly through our radars, we are measuring and updating their orbits. And I've just increased the speed of the system here. Currently looking at around about 20,000 objects in low Earth orbit, active payloads, defunct satellites, space junk, and big debris. And you'll see how these objects are moving in different inclinations. But every time we measure an object, we update the orbit of that object. This is what we call the state vector, and we propagate that state. And we then run an analysis of that object versus every other object that is in our catalog. And this gives us the ability to do our safety of flight function, and also our characterization of what different satellite systems are doing in low Earth orbit. But it's important to point out here, what we are tracking at the moment is correlated to the US Space Surveillance Network. And basically, that network is tracking objects at 10 centimeters and above. So fairly large objects. And as I said earlier, we're aiming to increase our radar density, if you like, around the world to enable us to start really reach the performance of the radars and start to track smaller and smaller debris. From what we can measure, we know there's around about another 250,000 objects in the 2 to 10 centimeter class, which are currently untracked. We call this lethal non-track debris because it's all traveling at 27,000 kilometers per hour. And of course, at that speed, its momentum is catastrophic to any collision. A golf ball at 7.5 kilometers per second is going to destroy anything it hits in low Earth orbit. So this is a great challenge. We call it the data deficit of low Earth orbit, and certainly something we're trying to address with the further build of radars and deployment of these radar systems around the Earth. On our side of the Earth, see the contribution of the Kiwi Space Radar. Fairly important radar system for us. One of the good things to mention about this radar is we commissioned it in November 2019. It's an autonomous system, that is, it's not manned. We operate it remotely. And because of the pandemic, we actually didn't have anyone servicing that radar from LeoLabs until just recently. I had a couple of engineers go across there and do some maintenance on the radar. So with these solid state type radar systems, you can see that they're very reliable. And we haven't had too many issues with them. And it gives us the ability there to operate them remotely and scale the radar systems. I'm going to take you now to how do we use this data. And really the thing I'll show you is the conjuncture analysis toolset. So as I said, every time we measure an object, and in fact I should just talk quickly about the stats, we're taking about 480,000 measurements a day from those 4 radar sites. We are updating the states of the 20,000 objects in low Earth orbit, about 35,000 radar passes of catalogued objects per day and updating those orbits. And our radars are tracking at both range and Doppler. So they're calibrated, the S-band ones are calibrated to 20 meters and 0.2 meters per second. So our resolution of a object in low Earth orbit is in the order of 20 to 30 meters uncertainty. And that sort of resolution is really important when you actually start to calculate things such as conjuncture risks and these type of behaviors. So at the moment, I'm showing you the conjunctions that we're calculating over the next 7 days based on that continuously updated data. These are all the heat balls. What I'll do is reduce the probability of collision down to 1 in 10,000 or less, and look at what we call the critical conjunctions. And you can still see there's a number of critical conjunctions that we're basically estimating will occur in the next week around the Earth. I'm going to try and find one that I can detail to you. I had a few candidates here earlier. And obviously the polar area is a really an area of greater conjunction than anywhere else. And something that obviously with obviously the satellites do converge a bit. One of the biggest issues in low Earth orbit is things such as the derelict rocket bodies and the debris fields from previous weapons tests and other breakups. So this one here we'll look at is an SL-8 rocket body with a bit of debris from Feng 11C, which was a debris field caused from the Chinese direct-to-send ASAT in 2007. What our system does is continually calculates the geometry of this conjuncture. And basically conjunctures, we sort of say it's like two, high-speed vehicles approaching an intersection and no one's going to stop. It's really a matter of physics as to whether they're going to collide or not. But this will show you the geometry of the situation here and the calculations that we're making about the actual probability here. In this case, reasonably high conjuncture risk, 6.1 by 10 to the minus 4 and 147 meters. But if we go into the way this is done in the reporting, we'll show you that basically we are measuring both objects every pass with our radar systems. We're updating their orbital states. And then as we go from 7 days down to the time of closer approach, TCA, you can see we're usually reducing the uncertainty and starting to resolve the criticality of the conjuncture, both in miss distance and in probability of collision. Unfortunately, this one is trending in the wrong direction as the probability is increasing. Now, remember back to the heat map, and I said, okay, we're tracking 20,000 objects in low Earth orbit and working out conjuncture risk of every object versus every other object. But also remember I said that in catalogue at the moment, no one is tracking the 10 to 2 debris field, which is also critical. So we would expect 9 times the amount of conjuncture activity will appear as we start to solve this data deficit problem and increase the capability by building and deploying more radar systems. So this could be a very interesting future for us. Just going to let this one build as well, and let's talk about our future radars. No, I don't. I'm on the right screen, sorry. Too many screens open. But at the moment, we're building a number of radars around the world. We've just finished construction on the one in the Azores, mid-Atlantic, so the one closest to Europe for us. And we're in test at the moment on that radar system. And that'll be our 5th site. You can see this is our test platform here. So you can see it's another dual radar system. That orientation and increases coverage on that side of the Earth, of course. But I'm in Western Australia at the moment. I've just been to our WA site down near Collie, if people are familiar with the region, in the southwest of the country, where we're building our 6th site, 9th and 10th radars. And again, S-band, phased array, one-dimensional systems. And I'm pretty excited about this because increases the coverage of the southern hemisphere, of course. And what it really does is it'll work very much in conjunction with the Kiwi space radar. If you realize, for example, especially high inclination or sun synchronous traffic in low Earth orbit is going pole to pole. And of course, the Earth's rotating east. Objects that the Kiwi space radar is seeing and discovering, if you like, will be handed over to the West Australian space radar. And this is the way we plan to give us the opportunity to do more discovery and start to populate our catalogue with smaller and smaller debris. I know I'm going to get a question of why 2 radars in one location. Well, you can see that these red bands are the field of view. So we're measuring an object as it flies through. If it's a new object or an object where we want reduced covariance, the radar networks it to the next radar and checks that object and updates the orbital state. And this is the way we're actually aiming to discover new objects. And then we're going to propagate that object through our cloud-based astrodynamic system to the next radar. And again, look for it in the right time and space on the first of the radars that we'll see it, then the second radar, and now we get near certainty that it is a real object, and we can start to look at looking at cataloging what's going on. And maybe a way to explain the value of that would be to look at the Cosmos 1408 debris field, which we're tracking at the moment. It used to be about 1,500 trackable objects in low Earth orbits, now about 900. Quite a few have already deorbited. But you remember this event last November? We actually picked it up on the Kiwi space radar. First up, that was the first pass we had, and we could see it was no longer one satellite. There was a number of objects where the satellite used to be. And then we went into different modes to actually start to track the debris field. And the reason I bring this up is because events like this, breakups in space and other such things, with both the Kiwi and the West Australian space radar working fairly close in time and space, if you like, to each other, we're going to get a bit more opportunity to bring this data into our catalogue a lot earlier than we previously have. So this is the value of distributing and building more radar systems around the world. So with that, I will stop sharing screen and hand back to Brendan, and I'll certainly be ready for any questions.
Great. Thanks, Terry. Much appreciated. Fascinating brief. So now we move into our question and answer session from our speakers. So again, if we've got a couple of questions in the Q&A. If you've got others that have come up from the discussion, if you can enter it in the Q&A window at the bottom of your Zoom screen. So we do, as I said, have a couple of questions. I guess the first one, Yvonne, was for yourself, which was in regard to the observatory at Whangaparoa. The question was around how long has it been up and running, and are you able to comment on any planned or potential capability or equipment upgrades you might be considering?
Yeah, thanks, Brendan, for this question, because I forgot to mention during my talk that, yes, we are actually, well, first, the observatory has been around for what, maybe 5 years now, but we are in the process of an upgrade, and the whole site has been upgraded. We have a new building, which will be operational towards the end of this year. But the major upgrade will be a faster tracking mount that will allow us to do faster objects in low Earth orbit. So that's all hopefully going to happen towards the end of this year.
Great. Thanks, Yvonne. And for Terry, I see you've spotted the one on the visualization tool. I'll leave you to respond to that one.
Thanks. I'll actually just display that again. They were actually, I'll come back up here in a moment. And I'll just leave Cosmos 1408 debris field up. So these red slices or stars, if you like, are actually the fields of regard of the radar. So here in Alaska, this is a two-dimensional radar. It can search north, south, east, and west across the sky, and in range, of course, as well. So two-dimensional. These other radars, these slices, are one-dimensional. That is, they're searching across that field of regard, phased array technology, meaning electronic beamforming. And this is what we call a space fence. So we're actually waiting for objects to fly through them and then taking measurements. And we've got two in one location there to get the opportunity to measure twice. So it's a very efficient way of operating a radar system in low Earth orbit. And in fact, what you're really doing is allowing all objects in orbit to scan themselves. We let them come to us and then take the measurements as they fly through the fields of regard. So yeah, that's the difference. And you can see, I think the other question is, how long is it going to take us to start to be able to catalog, if you like? It's really about cataloging, tracking and cataloging smaller debris. Well, what I can tell you is, I mentioned earlier that we are now using our radars to measure some of the smaller debris. That is, we can see them. We can see them fly through the radars. We get the tracklets. We know the debris field is there. The problem really is cataloging and tracking, which means that we could propagate in orbit, but we need to be able to see that object again a number of times with certainty to actually say that that is the same object, the same golf ball in space, if you like. And really what we're doing at the moment is increasing our radar distribution and radar capability to do so. So we're pretty excited. I think once we get the Azores online, West Australia, we've got another one being built on another continent we haven't actually publicly announced yet, and plans for up to 4 radars per year being built elsewhere around the world. You'll start to see us be able to take on this challenge and start to track the smaller debris and catalogue that debris. So that is probably only 6 to 12 months away from when we actually start that process. The radars are ready, we just need more radars. And it's simply a radar distribution issue at the moment. You have that certainty of being able to catalogue an object in low Earth orbit. Hope that answers the questions.
Thanks, Jerry. I think that does. I guess a question that's come up, and perhaps we broaden it out. Is there? We've talked about collaboration, and Terry, I know you're an advocate for collaboration across industry, defence, academia, etc. There's a question around, are there opportunities for collaboration, I guess, for university researchers? And I guess noting we've also got other industry players online. Are there broader commentary you could make on potential of either areas that might be opening up or areas of interest that industry or academia can support with? Jovan, I know you're working with Auckland University. Any comments from your perspective?
Well, I think there are great opportunities for collaboration, and what we are doing with Auckland is one example, a very successful collaboration between like observational part and analytic data analysis part by a team of orbital dynamic experts. So we would like to continue that, and we are looking at other options as well. So there should be, and we are a small country, and there is much gain to in this idea of into the idea of collaboration instead of doing just everyone by themselves. So I will definitely look into more opportunity to collaborate with universities.
Well, Brendan, piggybacking on that, I suppose collaboration is I think very important for the success of our national space industries. We really do have a lot of capability that we can bring to bear if we do collaborate commercially and with research institutions. In fact, I'm off to Curtin University after this session today to talk to them about what we're doing. One of the collaboration areas we're looking at is working with some of the other sensor providers to where we very much concentrate on the objective data of objects in low Earth orbit. Other sensor providers can add other characteristics, the orbital inspection capability, what does the satellite actually look like as the solar panels deployed, these sorts of questions, and whether the site is active or not, that is actually transmitting if it's an active satellite. So collaboration in that sense gives us, I think, more opportunity. And then in the research field, we are actually supporting the University of New South Wales and University of Adelaide in a trailblazer bid, which they've been successful with. And that's more to develop some of this multi-sensor space domain awareness or space situation awareness capability here in Australia. But the other one we'd like to see is innovators looking at how they can use our data sets and actually create new products, new ways of operating in the space environment. We're pretty excited about that. We call ourselves Google Maps for space because we're concentrating on this 3-dimensional live mapping product, which is data rich. But we know if that's, we can build other applications on top of that, such as, like a Waze for space or Uber for space or other mission systems. And that's what we're aiming to fuel, that sort of innovation and growth in a digital economy, which is very much, underpinning space. So there's lots of opportunity for collaboration.
I'm not so sure about Uber for space, Terry. Some of our experiences with Uber, but yeah, no, that's fascinating. Thank you for that. We've got another question here that was a query around the differences of SSA for GEO and LEO. Jovan, I know you're interested in responding to this. Do you want to make any comment on that?
Yes, because I have had experience with both, and from a point of view of an optical facility, of optical sensing, there is a big difference in terms of how easy or how difficult it is to do the tracking. Low Earth objects move fast in the sky, in your field of view of your instrument. You need to have very accurate tracking. The whole passage lasts only for a couple of minutes. You have to be very organized, not to miss a single part of that transit of an object over your location. The passes happen at irregular intervals. You sometimes wait for a week to see an object. Sometimes you can see 2 passes in one night. It has to be only when the sky is dark enough so that you can see your object, but your object is still lit by the sun. So it's a very tricky situation where you can only observe in a very narrow window, and it can take a lot of time to get enough data in LEO. But geo objects are easy. They hang out there on the sky for the whole night. You can see them whenever you want, whenever it's clear, whenever it's convenient. You can take hours looking at one object. So it's much more easier from an optical point of view to look at geo targets.
Thanks, Joel. Terry, I don't know if you wanted to add to that at all, or from your perspective?
Well, horses for courses, so to speak. Low Earth orbit is ideal for radar, basically. Radar has obviously a physical limitation in terms of being able to get energy out and back, the tyranny of the R4. But it's ideal for low Earth orbit. It's ideal for this very congested space traffic problem that's occurring in low Earth orbit. Why? Well, it's 24/7, 365. We're not weather dependent. The radar is a persistent sensor that's doing this work. So it is ideal for low Earth orbit in that respect. And of course, we don't mind tracking rates, very high tracking rates coming across those radars, but we only really need a small time to measure and gain the accurate information that we need to update the orbit of an object. So it is an ideal area for radar to operate, especially phased array. Now, the big difference between phased array, and I need to point this out, and mechanically scanned radar is the capacity of a phased array radar system. The ability for it to search across very large fields of regard very, very quickly and cover a lot of space, basically, and actually produce a lot of data. One of our radars actually will be able to take about 2,000 measurements an hour, and really it's super agile. Within 10, 20, 30 milliseconds, depending on the radar type, those beams are moving up and down that field of regard to look for objects as they come through the space fence. So yeah, radar is very good for low Earth orbit. Great challenge to use radar in the higher orbits, much bigger radar systems. Really the regime of radio telescopy more so than anything else. But we're thinking about that. We'll probably come back in a few years with some scaled up radar systems to look at deep space.
And perhaps for the final question, that perhaps leads nicely into one we had, which was, respectively, what do you see as sort of key enablers or developments that people could see looking forward in space situational awareness? That you could comment on. Are there any sort of key technology enablers or things you expect might change in the next sort of 5 years that will influence how we might be tracking debris, or I guess even to that extent other challenges with, I guess, increased utilization of space and the challenge that might bring with it?
Yeah, so especially low Earth orbit is scaling. At the moment, 10 years ago, there's like 450 active satellites in low Earth orbit. I lose count. I think it was like 4,500 a few weeks ago. It's probably about 5,000 active satellites now. We're expecting in the order of 50 to 100,000 active satellites in low Earth orbit by the end of the decade. with a growing debris field and also space junk and other issues, it's becoming what we say is a big data problem. And really the key technology that I really didn't talk about is cloud computing for us. At the moment, our 4 sites, 6 radars are pushing at about 500 terabytes of data a day. And that's being going into the cloud there to be brought down to about a gigabyte worth of product, which I've just shown you some of the products that we deliver. So that is a big data, big computing problem. And we're scaling with that, the changes in the computing industry, both at the edge with our edge computing and then cloud computing. So I think the prospects of keeping up with the challenge for us are good, given the continual improvement of digital technologies and chips and other sorts of things that go into our electronic systems.
Great, thanks, Terry. Jovan, any commentary from your perspective?
It's quite obvious to me that tracking a large amount of objects and maintaining huge catalogs of objects is only possible with the radar technology at the moment. Optical sensing can never compete with that amount of data that radar can handle. However, the importance of optical sensing is clear, and I would see how simply increasing the number of optical stations, just multiplying reasonably cheap optical stations, observatories, and placing them around the country or around the region could enhance the ability to track objects and provide more data, more information about objects passing over us.
Thanks, Jovan. Well, it's certainly been an interesting challenge with, as you said, Terry, with the increasing, we hear congestion within space and the increasing complexity of, commercial launch and CubeSats, et cetera, is only going to make things more challenging and more interesting, I guess, and more things in space. I did note recently an article on SSA was also talking about putting more things in space to monitor space, which was kind of curious. But anyway, look, thank you very much, Jovan and Terry, for sharing your insights with us today and for talking about your experiences with DTA and LeoLabs. I'm sure everyone's found it fascinating. I certainly have. And thank you also to our audience for listening in and for your attention. If you've got questions, folk, or comments or any feedback for the speakers or on the webinar series, please don't hesitate to reach out and connect. Our contact information is displayed here on the slide. You'll also find us on LinkedIn, and you'll also find the series recorded and available on the Beca YouTube site as well. So thank you, everybody. Again, thank you, Jovan and Terry. Really appreciate your time. Happy Matariki Day for New Zealand, the first of its kind. So I hope everyone enjoys their Friday off there in New Zealand. And take care, everybody. And thanks again. Thank you.